Okay, so I want to talk a little bit about proofs. Now, I know that like in your reading, you've had several topics that you've looked at. For instance, you looked at prime numbers, right? And kind of simultaneous to that, we looked at Euclid's proof of the infinitude of the primes. That was also in your reading, yes. You also have looked at things like the irrationality of certain numbers, yes. So irrational numbers. That is something that we will look at more closely later on. We've even looked at things like encryption and decryption, okay, at least at a rudimentary level. They haven't really, what I would say, given a rigorous argument for why these encryption, decryption schemes are working, especially the RSA scheme. But eventually we'll actually move toward that. But in order to do that, we have to really delve into what it means to actually give a valid proof for something. Okay, so we're going to start looking at some basics of proof, and even some of the examples that we'll look at will be somewhat along the lines of what you guys read in The Heart of Mathematics. Okay, hope you've seems like you guys have been enjoying that book for the most part, which is a good thing, and we'll kind of build on what's going on in there, look at things maybe a little bit more deeply than they did in there, although we might have a few less jokes. There's some good jokes in there for sure, good math jokes. Hey, here's a math joke. You want to hear a math joke? Okay. What did 0 say to 8? Nice belt. That one took a while, but yeah, there you go. Nice belt, yeah, okay. I have lots of those. So the most typical types of proofs you have are direct proofs, okay? And honestly, these kind of follow the modus ponens pattern, okay, where you kind of assume the if part and you move toward the then part, okay? It's a direct proof. Then you have what are called indirect proofs, okay? So if you have direct proofs, you also have indirect proofs. And that would include things like contrapositive. Sometimes you call that the contraposition. If direct proofs involve modus ponens, what do you think the contrapositive, what argumentative form do you think the contrapositive would take on? If direct proofs are modus ponens, what do you think contrapositive would be? Modus tollens. You assume the opposite of the conclusion and you work towards the opposite of the premise, okay? The hypothesis. Contradiction. We've already seen a couple of examples of that in Journey Through Genius, right? The Greeks were somewhat obsessed with this argumentative style. They called it, well, again, in the Latin, it's reductio ad absurdum, okay? This was a very typical technique that they would employ. What you do is you assume the opposite of what you want to prove, and you show that it leads to an absurdity, okay? Which means that the original assumption, namely that the opposite of what you want was true, was really not a good assumption. And really, the original thing had to be true, okay? We'll look at examples of that. In fact, you kind of already saw an example of this in the reading, did you not? In the irrationality of square root of 2 proof. You may not have detected it, but in that proof in your reading, they assumed, or what they did is they're like, okay, we want to prove that the square root of 2 is irrational. So what did they assume instead? That it was rational. And they showed that that led to complete, utter nonsense. Yes? So that's an example of a proof by contradiction. Sometimes I've met mathematicians that are really contradiction proof averse. They hate proof by contradiction. They have like sort of a skepticism for it. But let me just be honest with you, that is just silly, okay? It's totally valid as an argumentative form. We'll actually verify that when we get to contradiction proofs, okay? They're completely valid. And honestly, things like, how on earth are you gonna prove that the square root of 2 is irrational without sort of just assuming the opposite at the beginning? That's one example where it's like, there's not really any other clear path forward. You just assume the opposite. You assume that the square root of 2 is rational, and show that something is wrong, okay? So, and then we'll look at some other proof techniques. Proof by cases, where you kind of split things up into multiple cases and work from there. And then we'll do, sometimes we call them WOLOG proofs, which means without loss of generality proofs. Sometimes there's some specific thing stipulated in the proof, like, that, you have two numbers, X and Y, one is even and one of them is odd or something. And it's like, well, which one is even and which one's odd? And oftentimes it doesn't matter which one you assume is even and which one is odd. So you just say without loss of generality, X is even and Y is odd, okay? And I'm just gonna move forward from there. So a lot of times in the course of a proof, you'll say without loss of generality. That means you're not, even though you're getting more specific so that you can play with things in the course of the proof, you're not really losing any generality, okay? Existence proofs, proving that things exist, which is, kind of fun. So what you do is you say, look, I claim that this thing exists, okay? And then what you actually do is show that it does, yeah? So it's like an existence proof, okay? So we'll look at those as well. These are the most typical types: direct, contrapositive, contradiction, proof by cases, without loss of generality, and existence proofs, okay? We've already kind of touched on some of these in the course of our reading and Journey Through Genius, right? They sort of gently lead us through some of that, except for the last proof, right? That one was sort of hard, right? With all the different parts and things. But in general, that book tries to kind of bring you along fairly gently. But Heron's proof, that thing was a beast for sure, okay? And then disproof by counterexample. So a lot of times, what you'll do is you'll say, okay, is this true? And what you do is you say, no, it's not, because here is something that violates that statement, yes? So you say, okay, is this statement true? You'll say no, because here's an object that actually violates that. Does that make sense? So, so what if I said something like, all real numbers are positive? In your mind, you just laugh, right? But it's because you have a counterexample in your mind. Give me a counterexample. Negative, okay, you guys gave me several. -1, that's my counterexample. -2, that's my counterexample, right? So you disprove that crazy statement I just made by actually providing a counterexample to that statement, okay? What is a proof? Well, sometimes it's that which strikes fear into the heart of geometry students. I remember I took geometry in 10th grade, okay? And I remember everybody that had taken geometry before me would say, oh man, just wait till you get to proofs. It's gonna be, it's gonna be brutal. And everybody kind of is afraid of that word as it pertains to mathematics. But again, we're just gonna gently kind of move forward with this. Hopefully it'll make sense. But in the end, a proof is just a valid argument that shows the truth of a statement, okay? Now, we were kind of really doing formal symbolic logic proofs, basically, yes? So like we did the thing with, the home by sunset example. And what we did is we were like, boom, 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 boom. We had all these symbols that we were kind of going through. That might have reminded you somewhat of, did you guys ever do like table proofs in geometry where it was like statement, reason, statement, reason, statement, reason? That's pretty formal, okay? That's sort of a formal English version of like the formal symbolic proof that we gave, last Wednesday when we went through that example, yes? But the proofs we're talking about here are more informal. It's more like a story. You kind of tell a story, you're writing sentences, yes? You're kind of saying, okay, this follows from this, and therefore this. And then we can do this, and therefore that, yes? And you just kind of talk your way through it, and you try to bring the reader along as you do that, okay? More than one rule can be used in a step. Okay, so a lot of times you won't even realize it, but you'll be applying multiple, rules of inference in one step. You don't always have to state which rules you use. And in fact, eventually you just abandon that completely because everybody kind of knows what rules there are and if what you're doing is valid. Does that make sense? So you don't always have to say, I am now doing existential instantiation or universal generalization. In fact, eventually you just forget those terms completely, which I don't know if that's good or not. But mathematicians eventually just kind of know, oh yeah, that's valid, that's valid, that's valid, that's valid. Even though they may have lost the terminology. And generally speaking, I would say that the informal proofs we're going to be doing are a little bit easier to understand, okay? But they're also a little bit easier to make a mistake because you don't have like the rigid formal symbolic logic flow, okay? So sometimes you might be prone to make a mistake or two, okay? So here's kind of our starting points. These are our bedrock anchor for our proofs. You have definitions of things. So like, you can't really argue with a definition. If I like tell you, this is the definition of this, you can't say, no, it's not. Unless, you happen to be right about that. But technically, most of the time, mathematicians have sort of agreed what the definition of something is, okay? So like if I say an odd integer, do we all like agree what the definition of an odd integer is? Yes? You can't just like Grant can't all of a sudden say, actually, I disagree with your, with the world's definition of odd integer. I think it should be something else. We would all just go, well, sorry. The definition is the definition, right? I mean, we've all sort of agreed on this. And like even integer. By the way, how would you define, this is just interesting, how would you define even integer? One which is, okay, one which is divisible by 2. Okay, so let me tell you a little story. There's this movie called Little Man Tate. Have you ever seen that movie? It's about this, it's a true story about this like boy genius mathematician, okay? And the way they found out he was a genius was like he was in first grade or something and he was sitting in the back of the room like bored all the time. And the teacher said, okay, class, or maybe he was in second grade or something. Okay, class, which of these numbers is divisible by 3? And Fred Tate, this, little man Tate or whatever his name is, he's sitting there kind of doodling and the teacher goes, Fred? And he goes, all of them. Why? Why, without even looking up, he said all of them. How would he know that they're all divisible by 3? Because any number is divisible by any number, right? Does that make sense? But what do you mean divisible by 3? Right. So, divisible by 3, meaning that it's like integer divisible by 3. So there is no remainder when you divide by 3. Does that make sense? But when you say even, you mean perfectly divisible by 2. That right? So you say a number is even if it is perfectly divisible by 2. Yeah? And that is the definition, yes. And we'll kind of formalize that eventually. So what about oddness? How would you define oddness of an integer? Not divisible by 2. I guess you could say that. How would you say that formally? Like what would the remainder be if you divided by 2? 1. Yeah? So as a remainder 1, if you divide by 2. Okay, that is something that we'll kind of grab onto eventually here. Okay? That's like an example of a definition. Theorems. Okay, sometimes you call theorems different things. Typically you don't, like the word theorem is like a crown that you put on something, yes? You don't want to just put crowns on anything, you know what I mean? Even if it happens to be something that's true and important. So theorem is typically a word that you reserve for really like big deal results, okay? There are other smaller things that you tend to not call theorems, but technically speaking, they're all theorems, okay? All these things that you happen to prove are theorems. But I'll talk about some of the other terms that you'll use for these things. Axioms, okay? Axioms are things that you're kind of assuming at the beginning, sort of self-evident, you know, self-evident truths that you're not going to prove, okay? So definitions, theorems, which you've already proved in the course of your work, axioms, which are kind of the starting point, self-evident truths, and what else are you allowed to use? Oops, what in the world did I just do? Oh, there we go. I kicked one of the buttons, okay? And then, of course, in the course of your argumentation, you can use the rules of inference, okay? That's what you use the rules of inference that we've been talking about. Okay, any questions so far? I'm just kind of laying the groundwork here, but any questions? Any questions? Okay, I said that theorems are known by other names. Theorems technically are things that you have proven from the definitions and the axioms by using the rules of inference, right? So let me go back one. Theorems are proved from the definitions, axioms, and by using the rules of inference, yes? You prove these theorems. But then the theorems become things that you can use, yes? Because you know that they are true at that point, and those things can then be used. But like I said, there are other names for lesser theorems. There's a lemma, which is kind of like a baby theorem, okay? There's a corollary, or if you take a class with Roper, corollary, I think that's what he calls it. It's like the British way of saying it. Yeah, I can't even do that. Okay, corollary. Corollary. A corollary is something that is like almost just totally obvious after you've proved something else. Does that make sense? Like you almost don't even need to prove it after you've proven this other thing. It just follows easily from something you just did. A proposition is sometimes you'll say proposition, and that's, you know, that's kind of like a lesser theorem of sorts. It's typically, the proof isn't very long. And then a conjecture is something, okay, well, let me just ask you, what is a conjecture? What is a conjecture? Well, it's something that you think, okay, right, so something like that. So a conjecture is something that you think is true, but that you don't yet know how to prove. Does that make sense? So like, I think this is true. You kind of write that down as a conjecture, but do you know it's true? No. So it's not a theorem. It's kind of like a pre-theorem, yes? It's a preliminary theorem. It's something that you think is true that has not been proved. We've talked about some conjectures before, like the twin prime conjecture, yes? Which is still a conjecture, but is getting closer and closer to being proved, yes? Right, so that was touched upon in the Heart of Mathematics also, although the book seems to be behind the times a little bit in terms of where that stands currently. And the twin prime conjecture is actually fairly close to being proved. Do you remember what the distance is so far? Like 6, right? There are infinitely many pairs of primes that are almost 6 apart, which is remarkable, okay? All right, so let's talk a little bit about proving theorems, okay? Oftentimes, the universal quantifier is flat out left out, okay? And what you're typically doing is you're proving, like, for all x in whatever domain I'm talking about, for all x, p of x implies q of x. So if this, then this. For all x, if this statement involving x, then this other statement involving x has to be true. Okay? But instead of like explicitly writing out the universal quantifier, what you do is you like take an arbitrary element, okay? And you actually prove it for that arbitrary element. like some arbitrary element C, and you kind of work with that specifically. What does that kind of remind you of? What does it seem like we're doing when we do that? Like, how can we, if I just prove P of C implies Q of C, how on earth am I able to then conclude that really the universal statement is true? If I know that P of C implies Q of C is true for an arbitrary C, how do I know that the universal statement is true? What's that called? That's called universal generalization. Yes? That was one of our special, techniques. Okay? So I prove P of C implies Q of C for a particular C, and I'm able to conclude that actually the universally quantified statement is true from that, and that's called universal generalization. Universal generalization. That's what's going on. Okay? Right, because how on earth am I going to actually go and verify everything for every X? I may never finish. Do you understand? Right, if it was some statement about like the real numbers, for instance, clearly I would never finish because there's infinitely many real numbers. Yeah? So what you do is you kind of start with an arbitrary real number, and you assume something about that arbitrary real number, and you show that the statement Q is true for that arbitrary real number. And then you know that since it was arbitrary, really, you've kind of proved the universal statement. Okay? All right, you guys ready to do a little example here? Let's do a little example. You guys ready? Just want to make sure. Okay, all right, let's do it. Okay, use a direct proof. So when I say direct proof, what are we thinking? What argumentative style? Modus ponens. You assume some kind of if part and you work towards some kind of then part. Use a direct proof to show that the sum of two odd integers is even. By the way, do you believe that? I mean, just think about some examples. This is what mathematicians do all the time. You'd be surprised how much time mathematicians spend just thinking about like baby versions of what it is they want to prove. Okay, so for instance, like 3 plus 5, right? Those are two odd integers, yes? But 3 plus 5 is 8, which is even. Yeah? And you do a couple of other examples, and you guys say to yourself, good grief, what about like negative odd numbers? So like, negative 3 plus 5. 2. Hey, that's even also, isn't it? And then you kind of play around with this for a while, go over to Chuck's and you add a few odd, pairs of odd numbers together, and you consistently find that every time you do it, you get an even number. So then you make a conjecture, like this one. The conjecture is the sum of two odd integers is always even. Okay? And now we have to actually find a proof. This is still a pre-theorem, yes? And that, by the way, this statement right here probably wouldn't rise to the level of a theorem. we might call this like a proposition, or if it's something that's going to help us towards something else, we might call it a lemma. Okay? But a theorem, that's a little strong. Okay? But sum of two odd integers is even. But in order for us to even start down this road, we need to have a rigorous definition of evenness and oddness. Now, we've already kind of said it out loud, yeah? But we need to think about how to formalize that more carefully. So how do we formalize perfectly divisible by 2 formally? How do we formalize perfectly divisible by 2? What do you think? Like that, so that's what we said even would be, yes? So help me out here. How would you formalize perfectly divisible by 2? So a number x, or an integer x, is even if it is perfectly divisible by 2. So what would that mean mathematically? Yeah. Yeah, That's exactly right. So x over 2 is another integer. Yeah? And Anna actually said n, right? So x over 2 equals n, some integer. That's the same thing as saying that x is equal to 2 times n for some n. Does that make sense? What Anna said is x over 2 is equal to n for some integer. But that's the same thing as saying that x is equal to 2n for some integer. Yes, that's what evenness means. What about oddness? Just same thing, but plus 1. Does that make sense? So x is odd would mean that x is equal to 2 times some integer plus 1. That's the form it would have to take on. So for example, so x is okay. Okay, so like 5 is odd, correct? So how would you write that as 2 times some integer plus 1? 2 times 2 plus 1. What about 11? 2 times 5 plus 1. What about, okay, here, I'm going to throw you a curveball here. What about negative 3? Ooh. 2 times negative 2 plus 1. Because 2 times negative 2 is negative 4, plus 1 gets you to negative 3. Does that make sense? What about negative 9? 2 times negative 5 plus 1. You see this? Every odd integer can be written as 2 times an integer plus 1. Similarly, any even integer can be written as 2 times some integer. Yeah? Okay, so let's formalize that. Okay, here it is. And I use different letters, but same idea as what Anna was leading us towards. The integer n is even if there exists, okay, there's sort of the existential quantifier. Do you see what I'm saying? If there exists an integer k such that n is equal to 2k. That make sense? Okay, the integer n is even if there exists another integer k such that n is equal to 2k. Yeah? That's what we were just doing, right? So like 8 is even apparently, yes? So does there exist another integer such that 8 is equal to 2 times that integer? Yes, sir. What is it? 2 times 4. Does that make sense? So in that case, n was 8, k was 4. You see? Okay, 26. 26 is even. So if n is equal to 26, what is the k that exists that kind of fits this definition? It would be what? 13. 26 is equal to 2 times 13, yes? Okay, so the integer n is even if there exists an integer k such that n is equal to 2k. And n is odd if there exists an integer k such that n is equal to 2k plus 1. One more than a multiple of 2. Make sense? We already were doing this. So 29, is that odd? Yeah. Well, okay, so if n is 29, what is the k? 14. 29 is equal to 2 times 14 plus 1. Okay, what about 87? Is that odd? Yes. 87, so if n is 87, what's the k? 2 times 43 plus 1. Yeah, k is 43 in that case. Note that every integer is either even or odd, and no integer is both even and odd. Okay? And we'd be in big trouble if there was something that was both even and odd. Okay? Well, 0 is actually even. By this definition, evenness means it's 2 times some other integer. Now, 0 is equal to 2 times 0. Therefore, 0 is even. Okay? By definition. Make sense? What about 1? Is that even or odd? Odd. How do you write it as 2 times an integer plus 1? 2 times 0 plus 1. 0 is an integer, right? Okay. 2 times 0 plus 1. Okay, what about negative 1? How would you write negative 1 as put it in the form 2 times something plus 1? 2 times negative 1 plus 1. Yeah, there you go. Any questions on this, please? Now remember what we were trying to prove? Or what our conjecture was? It was that the sum of any two odd integers is always even, okay? Use a direct proof to show that the sum of two odd integers is even, okay? So look, think about this with someone around you, okay? So think about it with someone around you and think about it formally, the way that we just did, okay? So like with the, if I have two odd integers, for instance, what does that mean? Like in terms of writing this stuff down in symbols. And what would it mean to show that the sum of those two odd integers happens to be even? So think about that with someone next to you and we'll reconvene in a couple minutes here, okay? All right, let's talk about this. And I'm gonna have to, let's see. How do I expand this thing? Oh, okay. Oh, maybe I need to just stop share. Yeah. Okay, so let's do this. All right, I'm gonna ask for a little bit of input here, but okay, so what are you guys thinking? So the sum of two odd integers is even. So how do we start this thing? You start with a couple of arbitrary odd integers. Is that what you're saying? Yeah? Okay. So let x, I don't know, x and y be odd integers. Okay? It's Maggie, right? Is that right? Okay. And you go by Maggie.
Yeah, I do.
Okay.
That is
Mark, yeah, okay. So okay, help me out here, Maggie. You said you wanted to write these in a certain way. So what does that mean? If x and y are odd integers, what does that mean? Yeah, that's right. So they're of the form 2 times something plus 1, yeah? Okay. Then, okay, there exist integers, okay? Now look, does the thing that, so x is going to be equal to 2 times something plus 1. Y is going to be 2 times something plus 1. Now you have to be careful. Don't use the same letter for both of these numbers. That makes sense? Don't say like x is 2k plus 1 and y is 2k plus 1 because then you will tend to think that x and y are equal. Does that make sense? They're not both 2 times the same thing plus 1. So you have to kind of divorce the two from one another. Okay? Then there exist integers, let's say j and k, such that what? Why do you think I put two integers here? So I even used like alphabetical into your j and k. So like x is going to be what? Yeah, 2j plus 1, and y is equal to 2k plus 1. Okay? Yes, that's a great start. All we've done so far is we've simply articulated what's true about two odd integers. And we've made sure to say, look, these guys, x and y are different numbers. So the thing that x is equal to 2 times whatever plus 1, and the thing that y is equal to 2 times some integer plus 1, those things don't have to be the same, yeah? So we've appropriately divorced the one from the other, okay? Now what? What are we going to do? Just add them together. I mean, what else are we going to do, right? We're just kind of following our nose here. So we say, note that x plus y, okay, Maggie, you're kind of in the driver's seat here. So x plus y equals what? Yeah, you just kind of sub in what they're equal to, 2j plus 1 plus 2k plus 1, which is equal to what? 2j plus 2k plus 2, okay, which is? Okay, which is what? Right, you just write it as 2 times j plus k plus 1, which, by the way, is 2 times an integer, which is the definition of an even number, yeah? Because it's 2 times an integer, yes? So x plus y is equal to 2 times an integer, right? So it's equal to 2 times the quantity j plus k plus 1. We just put comma and even integer. Okay? Okay, so x plus y is equal to 2 times an integer, which is even, yeah? It's twice something, twice an even integer, yeah? And by the way, that's the end of the proof. That's it. So what you do at the end of the proof, you know, since we have like a math organization, sort of write QED, sometimes they'll put a little box, you know, to like indicate the end of a proof. Some people develop their own little cool things to put at the end of the proof, but QED is, you know, that's kind of like a snooty way of ending the proof, right? Which, you know, hey, why not? It means quod erat demonstratum, which means which was to be demonstrated. Yes, Maggie. Hmm? Doesn't really matter. I just didn't want to use the same letter, right? Right. If I would have used k for both x and y, then technically speaking, I would be saying that x and y are the same number. Does that make sense? Okay. If I would have said x is equal to 2k plus 1 and y is equal to 2k plus 1, well, 2k plus 1 is 2k plus 1. Therefore, x and y would be equal. That would technically be a mistake. Does that make sense? Okay. So, yeah.
And it hinges on the whole proof being true in the first place, doesn't it? Because the n is odd, then you're just saying again at the end that 2 odds make it even.
No, I mean, all I did was I said, look, oddness means this. If I add these together, what happens? I just show what happens. I manipulated it and I showed that I ended up with 2 times an integer. But by definition, what is 2 times an integer? That's an even integer, which is exactly what we want. So, I mean, you just kind of followed the definitional trail. I wasn't, the whole time it was just like, I was just following my nose in terms of what the definition of oddness was. And we were led to something that is by definition an even integer. So we didn't assume anything that we were trying to prove or anything. Okay. All right. So that's the first proof in the books. I'm just trying to kind of introduce you to some of this, right? Roper is the one that will kind of push the limits later on, but there you go. Okay. All right. That's it.